So hello and welcome again in this natural convection lecture series. So in the previous lecture I have discussed about the case of Prandtl number much greater than 1, and we saw that the velocity boundary layer will be larger than the thermal boundary layer, and that is happening because of the relative magnitude of this nu and alpha. Clear? Momentum diffusivity and thermal diffusivity. So as you can guess correctly, now our case 2 will be Prandtl number less than 1. So case 2 will be Prandtl number based on infinity, that is much lesser than 1. Clear? So I told you that my 1 by Prandtl number, right? I can show you again that I already derived that my 1 by Prandtl number is this inertia by viscous, right? So what I can do is, that means from this analogy I can directly show you that if my Prandtl number is, so inertia by viscous force is much greater than 1, that means my inertia force is much more important than my viscous force. Okay, so I will neglect the viscous terms in the governing equations. So let me write the governing equation first. First governing equation will be the momentum one. Okay, so momentum, or I should be very specific, that is x momentum. Okay, I think, okay, this was only x, right? Let me, okay, so actually let me just copy the equations, otherwise it will take much more time if I have to write the equations again and again and again. Okay, so let me just copy the equations. So this is the momentum equation. Okay, so I will copy it. Paste it. Okay, fine. So now this is my viscous term, sorry, this is my viscous term, and these are inertia terms, and this is the buoyancy term. So I will neglect here this term. Okay, so this term will be neglected. Clear? That means what I will be getting is that my inertia force will compete with the buoyancy force. And what is the order of magnitude of the inertia force? Here it is correctly written, that is rho infinity uc square by L. That is competing with the order of magnitude of the buoyancy force, that is g beta infinity delta T characteristic into rho infinity. Clear? So this rho infinities will be cancelled out, and I can directly get my u infinity c as g beta infinity del T C L. Clear? So this is a very important result. You can see that the difference with the previous case is that here I have an equation for u where there was delta naught. Okay, so delta naught was there in this equation. Okay, so I okay, so I got this equation here, and you can see that here I was having this uc and delta naught, and that means if I have to express either this uc or this delta naught in terms of the known parameters, then I need one more equation, and that I got from the energy equation. Now this equation will still be valid because this I got from the energy equation, and this has nothing to do with the Prandtl number being greater or less than 1. Okay, but now in this case I directly got my uc in terms of the known constant parameters, and here there is no delta naught. Okay, but still I need the order of magnitude of delta naught. How can I get that? From the energy equation. Clear? So energy equation reads my uc or u directly u into del t del x plus v into del t del y is equal to alpha del square t, right, del y square. Clear? No other term. So you see delta dc by L. Okay, so you see that here these two terms, if you carefully examine, these will be of the same order of magnitude, because u by L is of the order of magnitude of v by delta naught. Clear? And now what I can do is, this is the order of magnitude of these two terms. Okay, and for this term it will be this delta Tc by delta naught square. Clear? If I now compare these two, I will be having uc by L is of the order of alpha by delta naught square. That means my uc is of the order of, or I would write that my delta square is of the order of alpha L by uc. Now I know the uc, right, the order of uc, that is g beta infinity delta Tc L and whole to the power half. So this will be equal to alpha L g beta infinity delta Tc L whole to the power minus half. Clear? Okay, so I want to find generally a non-dimensionalized number, that is this by L. So if I have to find this, I will divide the both side by L squares. Okay, that means it will be L and again g beta delta Tc L whole to the power minus half. Clear? Okay, so now let me see that if I can express this term in terms of a well known number or not. Clear? So see, g beta infinity delta Tc, okay, g beta t delta Tc L cube by nu square. This is my Grashof number. This is my Grashof number. Okay. Now here in this whole to the power half, I will keep it like that. So what I have done is, with this term I have multiplied 1 L square above, 1 L square below. That means I have to bring 1 L square here and 1 nu square below. That means to cancel it out, I need to bring 1 nu square above, and the rest remains same, and there is one alpha by L. Okay, so that means I can get g beta delta Dc L cube by nu square whole to the power minus half. Now I will bring these things out of the box, out of the first bracket. Okay, so then it will become L by nu, because there was a minus half, into alpha by L. Clear? That means it is what? It is my Grashof number, okay, gr based on L, okay, and based on also the infinity state. So still I am writing only L, because we represent the numbers like Grashof number and the Reynolds number with the length scales, and this is Prandtl number whole to the power minus half, and that means it is, and you can write that as Prandtl number of infinity, because Prandtl number is a property of a fluid. Okay, so it is Grashof number into the Prandtl number. Okay, and that is our Rayleigh number. Okay, so Rayleigh number L whole to the power minus half, and that means directly I am getting that my delta naught by L is of the order of Rayleigh number whole to the power minus 1 by 4. Let us examine the order that we got for the previous case. Okay, so what we got? Okay, so I think we got the same thing. So did we make any mistake? Because there should not be the same order of magnitude. Okay, So this is okay. Let me see here. New square Grashof number into Prandtl number. So have I made any mistake? So L by nu, and it is nu by alpha Prandtl number whole to the power. Okay, I think I got the mistake. This is a very bad mistake. So here I am having, this is my Grashof number, this is my Prandtl number whole to the power minus 1 and not minus half. Okay, so sorry about that. Okay, so these are happening because I have not done my homework before teaching you. You see that every teacher or everyone, if he or she has to teach you, then he must or she must have done his or her homework. Okay, so I did not get the time for that, and I apologize for that also. Okay, so this is the thing, and actually what you can do is that you can bring this Prandtl number here, and that means here you will have this Prandtl number whole to the power minus half. That means it is Rayleigh number whole to the power minus half and Prandtl number whole to the power minus half. Okay, so this will be 1 extra Prandtl number whole to the power minus 1 by 4. So this is the order of magnitude. And similarly, if you have to find the Nusselt number, so that is what, H L by K, and that is again equal to H delta naught by K into what, L by delta naught, right? And I have already shown you that this is of the order of 1. That means your L by delta naught, this is of the order of the Nusselt number. That means your Nusselt number is of the order of Rayleigh number into Prandtl number whole to the power 1 by 4. This is the order of your Nusselt number. Clear? Now this was just the mathematics, but you have to visualize the thing. Again I will be drawing that plate, okay, and the coordinate axis. So this is my y direction and this is my x direction, and this is the origin. Clear? And the plate is again at a temperature of Ts, T surface maybe, and T infinity is the ambient temperature, and Ts is obviously much greater than T infinity. Not much greater, I have already told you that this temperature cannot be much greater. Okay, so now you have to see that I know that my Prandtl number is much less than 1. Clear? That was the case, I think, that I have started with. Yes. So if my Prandtl number is much less than 1, that means my nu infinity is much less than alpha infinity. Clear? Now what I can say is, that means again the same argument, if you have already followed the last lecture, you can easily understand. So this is my momentum diffusivity and this is my thermal diffusivity. So I am explaining again, okay, because this is a very important concept. That means my momentum diffusivity is what? Momentum diffusivity is a messenger who will tell you that, okay, my surrounding fluid molecule has encountered a change in momentum. That means I have to also change my momentum. Okay, so it is a messenger who will tell you if there is a kind of collision, if there is a kind of disturbance in the movement of the molecule. So how can we get the disturbance for the movement of a fluid molecule? By the presence of this wall, and we know that because of the nose deep condition, the molecules just at the vicinity of the wall, they had to be at complete rest. Now this is the change in the momentum, because the fluid was flowing like this in case of natural convection, flowing like this, and when they are coming at the vicinity of the wall, they are like, okay, now something is resisting me, and this message is being propagated in this direction by this messenger. Now the same thing is being done with the thermal diffusivity. So for the thermal diffusivity, what is happening, that here there is an abrupt change, that all here it is T infinity, but here is an abrupt change in the wall temperature, that is Ts. So the fluid molecules will know this change, that okay, there is something very high, very hot. So that means the fluid molecules who are at the vicinity of the wall, they will not bear this much high temperature, and they will not tell, okay, we will bear the whole high temperature and my friend molecule will be not that much in high temperature. No, that will not happen. This effect of Ts being very high than T infinity, this will be propagated in this direction again, and that is because of this thermal diffusivity. That means if my momentum diffusivity is very less, that means the message that this is that here is a no slip condition, this will not be propagated that much compared to the Prandtl number much greater than 1 case. Okay, so here, so when my Prandtl number was much greater than 1, okay, so here my momentum disturbance could have been propagated in a much larger distance, because my momentum diffusivity is much larger. Now these two layers will be almost coinciding. Okay, why I am saying it? Because you can argue with me, okay, if my alpha is now greater than nu, that means my thermal boundary layer should be should be very much larger than the velocity boundary layer. Okay, but these are the things where we need to be mature enough. Okay, so this is not like if A is greater than B, that means this is happening. That means if my B is greater than A, then just the opposite will happen. No, you cannot think like that. Okay, why you cannot think like that? So these things are very important if you are preparing for the interviews like BIRC, DRDO or ISRO. Okay, so here you have to understand that what is creating the velocities. The temperature difference is creating the velocity. That means if the velocity is not there, I can say that the temperature difference is not there for sure. Okay, but if the temperature difference is there, there will be surely a prevailing velocity. So let me show you this thing. So if this is my temperature boundary layer, if this is my temperature boundary layer, clear? That means within this region, okay, my temperature variation is there. Now where my temperature variation is there, that means the density variance will also be there, and if the density variance is there, that means the buoyancy force will be there. If the buoyancy force is there, there will be the velocity profile. Okay, there will be the positive velocity, there will be a non-zero velocity. The positive velocity term is not correct, but there will be a non-zero velocity. Okay, so here in the previous case, because the effect of the velocity could have been propagated at a much larger distance, that is why the velocity profile was something like this. The velocity profile was something like this. But now, as my temperature difference is being diminished, my velocity will also be diminished, because there is a very less alpha. So this molecule, okay, this molecule here will have a very less velocity, because here the temperature difference is also very less. But now this alpha, this nu is also very less, and that is why this molecule here will not get the message that okay, he has a very small velocity, that means I have to also move. Okay, and that is why the velocity profile will also almost coincide with this, and it will be having something like this kind of profile. I will draw it. Okay, so if I draw it here, so some maxima and then 0. Okay, then 0. So again I have drawn it. Okay, so firstly I will draw this. Okay, so first of all some maxima and then 0. Okay, and the temperature profile will be something like this. This is Ts, this is Ts, and this is T infinity, and this is your Vmax, this point. Okay, so now you see I can divide the region into two different kind of domains. Okay, so if I draw a straight line, okay, so here you see, here you are very near to the wall, that means here you cannot neglect viscous force. This is very important. Okay, so in turbulence also, in turbulence we say that my inertia force is much greater than the viscous force, but still there is a layer called a viscous sublayer, okay, very near the wall, because near the wall nothing can overpower the viscous forces because of the no slip condition. And here also, even if we are saying that we are neglecting the viscous force, but near the wall we cannot neglect the viscous force, and here actually the buoyancy force will compete with the viscous force. Okay, because buoyancy force we also cannot neglect in the natural in the natural convection. Okay, and in the remaining part, that is this one. So let me draw with a different color again. So this part here, now the viscous effect will be negligible, and in this part actually the inertia force will compete with the buoyancy force. So here the inertia force is there because the temperature difference is there and the buoyancy is there. Okay, so I think this thing is clear, and this kind of analysis, these are a kind of a feeling. Okay, right, like if my nu is much less than alpha, that means my momentum diffusivity is much less than alpha, then what can happen? To answer that, you need to know about that what exactly this momentum diffusivity does. Okay, so in DRDO I was precisely asked in the interview that what is Prandtl number and what is its significance. So like any other aspirant, I told that it can denote the ratio of the hydrodynamic boundary layer to the thermal boundary layer. Then they asked, no, you have to tell the difference of individual things like alpha and nu. Then I told like this, that alpha will define that up till how much distance the thermal nature or the temperature thing will be propagated, and nu will decide that up till how much a momentum disturbance will be propagated. So these kind of understandings are very necessary. Okay, so now let me continue. So we have completed the order of magnitude analysis, but the order of magnitude analysis actually gives us what? That is, my Nusselt number is of the order of something. Okay, that is, we just got that Rayleigh number into the Prandtl number whole to the power 1/4. Okay, this we got, right? Okay, but now the actual thing will be that for Prandtl number much less than 1, we will get my Nusselt number L is equal to some constant C into RAL, Prandtl number infinity into 1 by 4. Now we have to find this constant. This we can find in again two ways. One way is approximately, okay. Another way is exact solution. How can we find it approximately? This method is also called the integral method. And if you have already studied the boundary layer theory or my forced convection, okay, my forced convection playlist where I have in detail described the boundary layer theory as well as the forced convection. So here what we do is we integrate the governing equations and we assume some profile about which we need the informations, like for the boundary layer we assume some profile for the u component of velocity, that is the x component of velocity, and here we will assume some profile for the temperature. We will use that profile to find this nu, Nusselt number. So this nu is actually correlated with the temperature gradient at the wall, okay, the transverse temperature gradient at the wall, and that you can easily show. Okay, how you can easily show? I mean these things these things should be at your fingertip. So this is actually what, HL by K. Now your H is what? H is what? Q by delta T. Okay, and now what else? So this Q is what? Q wall. Okay, this is Q wall. So this Q wall will be your minus K, okay, at wall C. That is how you will get your temperature profile. And why this minus would be there, that I have explained in my previous videos in the forced convection, also in the advanced conduction playlist. Okay, you can also get rid of this minus, that is up to you. Okay, so now our next task will be to look for the exact solution. This is very interesting. Okay, exact solution. Okay, so here firstly we will not assume anything like that my Prandtl number is either less than 1 or greater than 1. No, we will not assume anything like that. We will not take any assumption on the Prandtl number. Only the incompressible fluid, the the properties of the fluid being constant, we will assume only these things. Clear? And then we will solve the governing equations. Okay, so better I will start this in the next session. Okay, because we have just completed the order of magnitude analysis, so we can start like a fresh thing from the next session. Okay, until that, goodbye, take care, and thank you.